Welcome to Semiconductor News Decoded. I'm Ty, with 31 years inside the semiconductor industry, bringing you the real view from the factory floor. Today's topic? ASE has developed a mass production line for 310mm panel-level packaging. In short, the shape changed from round to square, and now it can hold a lot more.
As always, I'll explain everything in the most simplified way possible. Even a middle schooler should be able to follow along. If you're a specialist watching, some parts may feel oversimplified, but I'd like to prioritize giving everyone the big picture first. Think of it as packing a lunchbox, and we just switched from a round container to a square one. So sit back and enjoy.
In one sentence, today's story is this. The lunchbox changed from round to square, and now you can fit a lot more food in it. Picture a factory worker packing components into a single container. For years, they used a round lunchbox. By switching to a square one, that same sized container can now hold far more. And that's the heart of today's story. A round lunchbox always wastes the corners. It's a circle. Those four corners can never be used. A square box, on the other hand, uses every inch from corner to corner. Why didn't we just use square boxes from the start, you might ask? The answer is the factory machines were designed specifically for round containers. Over decades, all the equipment and expertise was built around that circular format. Switching wasn't easy. But now, for the first time, there's a real path to making square boxes reliably and at scale. And that's exactly what today's news is about. Switching to a square lunchbox brings real benefits. First, you can fit more food. Just by going from round to square, the usable area increases dramatically. But there's more. Square boxes also work much better on factory conveyor belts. Square shapes play far more nicely with automated production lines than round ones. You can move more at once, processing speed increases, and the same amount of time yields far more finished products. But there's a problem. Square lunchboxes tend to warp. When heat is applied, different materials expand at different rates, causing the whole box to bend out of shape. The food inside can shift out of position, too. If a box is even slightly misaligned on the conveyor belt, it becomes a defective product. Preventing this is genuinely difficult. Whether you can control the warping, misalignment, and defect rate is the real test of whether you can truly master the square lunchbox. Round to square. It sounds like a simple shape change, but it's actually a major turning point, overcoming decades of accumulated technical barriers. Let's step out of the lunchbox analogy and look at what it actually takes to make the square box work in a real industrial setting. Let me summarize the lunchbox stance. A round container wastes corner space. A square one doesn't. But producing square containers reliably at scale requires solving a hard warping problem. That's a near-perfect map of where advanced semiconductor packaging stands today. The main player in today's story is ASE, Advanced Semiconductor Engineering, a Taiwan-based company and the world's largest dedicated semiconductor packaging and testing provider. ASE doesn't make chips itself. It takes finished chips and assembles them onto substrates to create usable products, what the industry calls back-end processing. What ASE has announced is a mass production line using 310mm by 310mm square panels for panel-level packaging, or PLP. And honestly, the current state of advanced packaging maps almost exactly onto this lunchbox story. To understand why panel-type packaging is such a big deal right now, you need to understand the state of AI semiconductors. The chips powering AI, like NVIDIA's GPUs or Amazon's custom silicon, can no longer rely on a single chip for performance. The dominant approach has become chiplets, combining multiple chips at high density inside a single package. And the key component at the center of that approach is something called an interposer, a middle layer that electrically connects everything together. An interposer is a relay substrate that electrically connects multiple chips. The standard for years has been a silicon interposer, literally made from semiconductor-grade silicon. But as AI chips have grown larger, so have these silicon interposers. Large silicon interposers are expensive to manufacture and prone to lower yield rates. ASE's PLP takes a different path. Instead of a silicon interposer, it uses a combination of RDL, redistribution layers, and small silicon components called bridges. It's a new approach designed to achieve both cost reduction and larger panel sizes simultaneously. ASE's packaging platforms, called Focus and Focus Bridge, are based on fan-out technology. Fan-out means encasing a chip in thin resin to flatten it, then rerouting the electrical connections on top. This has been ASE's core expertise, built up through years of packaging operations. The new 310mm panel line maintains compatibility with the Focus family while adding large area panel support and integration with automated production lines. It supports line space specifications of 2/2 micrometers and 8/8 micrometers, fine enough for the high-density wiring required by AI chips. Production start is targeted for the first half of 2027. For comparison, let's bring in TSMC, the world's largest contract chip maker, producing chips for Apple and NVIDIA. TSMC is also developing panel-level packaging under the name CoPoS, targeting mass production around 2028 to 2029. TSMC's CoPoS builds on its CoWoS technology, which is silicon interposer-based and is aimed squarely at maximum performance. ASE's PLP, by contrast, prioritizes cost efficiency and large area production. Neither approach is right. They're different paths that will naturally serve different customers and use cases. The real technical difficulty in PLP is not what most people assume. It's not about drawing fine wiring lines. The true challenges are three: warping, positional misalignment, and mass production yield. Every time a panel goes through heating and cooling, different materials expand at different rates, distorting the whole panel. Warping causes chips to shift out of position, and wiring connection accuracy drops. Managing this stably at production scale requires mastery of molding technology, yield management, and precision measurement and correction built up over years. ASE's ability to take on this challenge comes directly from the expertise accumulated through its long history of fan-out packaging work. Let's also take a look at Japan's efforts in PLP. Resonac, a Japanese materials company, leads a consortium called Joint 3, focused on advanced packaging, with 28 member companies. The goal is to cover the entire back-end supply chain within Japan: materials, equipment, substrates, and measurement. Based on my years of hands-on industry experience, I believe this ecosystem-based approach is one of the few remaining areas where Japan can genuinely win. Toppen, a Japanese printing and electronic materials company, has set up a pilot line at its Ishikawa factory, with planned operations starting in July 2026. The target technologies are organic RDL interposers, glass interposers, and glass cores, all directly at the core of advanced packaging. Fujifilm is also developing a PFAS-free PBO material called Z-Mates, with progress toward Damascene bonding process compatibility. These companies are not chip packagers. They supply the materials and substrates that make packaging possible. This is precisely the domain where Japanese companies can establish a durable competitive position. One more development worth watching: Rapidus. Established with strong Japanese government backing, Rapidus is aiming for mass production of 2nm class chips. Rapidus is now also developing RDL interposers using glass panels measuring 600mm by 600mm, significantly larger than anything we've discussed today. The math is striking. A reticle-sized large component that fits 4 times on a standard 300mm wafer can fit approximately 49 times on a 600mm square panel. Mass production is targeted for 2028. If achieved, this could fundamentally restructure the cost dynamics of back-end processing. The race in AI semiconductors has moved well beyond chip performance alone. It is now a competition in how you package them. No matter how fine the chip geometry gets, without the ability to package large numbers of chips at high density, low cost, and high reliability, the final product cannot compete. In this structural shift, I believe Japan's best path is building a back-end ecosystem centered on glass, materials, substrates, and equipment. Competing on raw packaging volume is a difficult fight against Taiwan, Korea, and China. But in the materials, measurement, and equipment technologies that support that production, Japan still has real strengths. The PLP format could become a genuine tailwind for Japan. As panel-level large-area production scales up, the importance of glass substrates, glass interposers, and glass core technologies increases. These are areas where Japan's expertise in optical glass and electronic substrates naturally applies. And as panels get larger, the precision required for warping and defect measurement and correction also increases, another area where Japan's measurement and equipment manufacturers have strong capabilities. The evolution of advanced packaging is no longer just a packaging competition. It is becoming a comprehensive contest of materials, measurement, and equipment. Let me bring everything together. ASE has developed a PLP mass production line using 310mm by 310mm panels, targeting production start in the first half of 2027. It takes a cost-focused approach, replacing silicon interposers with RDL and bridge components, and differs in direction from TSMC's CoWoS, with the two approaches likely serving different use cases. In Japan, the Joint 3 consortium, Toppen, Fujifilm, and Rapidus are all steadily advancing the back-end ecosystem. ASE was able to establish a path to PLP mass production because of the accumulated expertise in molding and yield control built through years of fan-out packaging. Technology can be published, but real-world capability can't be replicated overnight. For Japan, PLP can be a tailwind. The larger the panels become, the more critical glass, materials, measurement, and equipment become, and those are Japan's strengths. But a tailwind alone is not enough. To benefit from it, the pace of investment and execution must increase.
That's all for today. I'll keep bringing you semiconductor news and analysis, so if you found this useful, please like, subscribe, and I'll see you in the next video. This has been Ty on Semiconductor News Decoded.